Hello everyone, my name is Aryan and today I will discuss about Rao Blackwell Theorem. In my previous lecture, I have discussed about Kramer-Rao inequality, and we know that Kramer-Rao inequality provides lower bound of the variance of an unbiased estimator. Okay, that means minimum variance bound of an unbiased estimator. And here in Rao-Blackwell theorem provides minimum variance unbiased estimator for parameter theta or function of parameter tau theta. Okay, so that means in Kramer inequality provides minimum variance bound estimator, but in Rao-Blackwell theorem our main objective to find out the minimum variance unbiased estimator. So the statement of Rao-Blackwell theorem is let x1, x2, xn is a random sample of size n from probability mass function or probability density function fx theta, and let capital T be a sufficient statistic for tau theta. Okay, this is statistic for tau theta, and capital T1 be an unbiased estimator of tau theta. Then consider phi t is equal to expected value of T1 conditioning with capital T. Okay, then expected value of phi t is equal to tau theta and variance of phi t is less than or equal to variance of T1. That means if we are using sufficient statistic an unbiased estimator and defining a function by conditional expectation of t1 given t, then we get phi t, and phi t is again unbiased estimator for tau theta, and it has minimum variance as compared to t1. That means Rao Blackwell provides minimum variance unbiased estimator. Is it clear? Okay, so here I'm using two concepts. One is unbiasedness and second one is sufficiency. So I think you all already aware about the unbiased estimator and sufficient statistics. So this is the statement part, and now in next part I will discuss about the proof. Okay, so now come to the proof part of Rao-Blackwell theorem. So for proof of Rao-Blackwell theorem, again I have mentioned the statement part. So let x and y be random variables such that expected value of y is equal to mu and variance of y is equal to sigma y square. That means y is an unbiased estimator for mu. Okay, and let expected value of y given x is equal to phi x. Then we have expected value of phi x is equal to mu and variance of phi x less than or equal to variance of y. Okay, so this is the statement part, and now come to the proof part. Let fxy be joint probability density function of random variables x and y. Fx and fy be the marginal probability density function of x and y respectively, and fy given x be the conditional PDF of y for given x for small x. So such that fy given x is defined as fxy upon fx. Okay, we know that this is the formula for conditional density, and given that expected value of y given x is equal to phi x, so we can define this expected value of y given x by using expectation definition. So now this is sign of integration y density fy given x into dy, and right hand side is phi x. Again we are using equation number 1 and putting fyx is equal to fxy upon f of x. Okay, so after simplifying this, what we are getting? So here next step is 1 upon fx sine of integration y fxy dy is equal to 5x. So now you can see here, this is the expression which is free from the parameter, and our parameter is mu. So that means we can say that x is our sufficient statistics, because we know that the definition of sufficiency, if the conditional distribution is independent of the parameter, then we can say that the statistics is sufficient. So we are getting the expression is free from parameter, so that's why x is our sufficient statistics for mu. Okay, if x is sufficient, then we can take expectation of the both side of phi x, and phi x is this thing, and the left hand side quantity is expected value of y given x. Okay, so taking expectation, e of phi x is equal to e of e y given x, and if x is sufficient estimator, this is nothing but expected value of y, and which is equal to mu. This is the first part of the statement of Rao Blackwell theorem. Now the second part is the variance of phi x is less than or equal to variance of y. Then we will proceed for the second part of Rao Blackwell theorem. So now next step, variance of y is defined as expected value of y minus e of y ka whole square, and we know that y is unbiased estimator, then we can replace ey by mu. Then we are adding phi x and subtracting phi x in variance formula, and just considering y minus phi x as a first term and phi x minus mu as a second term, and expand this square quantity like a plus b ka whole square. So now you can see here, first term is y minus phi x ka square and taking expectation inside, then plus second term is expected value of phi x minus mu ka whole square plus 2 times of expectation of first term into second term. Is it clear? Okay, so first term I'm writing here as it is, and second term is what? This is the variance of phi x. So just we are replacing second term by variance of phi x, and again third term is 2 times of expectation of y minus phi x into phi x minus mu. Okay, and we have mentioned here second term is equal to variance of phi x because expected value of phi x is equal to mu. Okay, this is from part first. And now again I have mentioned here the third term. Third term is what? Expected value of y minus phi x into phi x minus mu. So just we want to find out the value of this term. So we can expand this term by expectation formula. So this is our first term, this is our second term, just like x, y. Okay. So sine of integration over x over y. First term y minus phi x, second term phi x minus mu. Joint density fxy dx into dy. Okay. And just simplify by using fxy is equal to fx into fy given x. This is from equation number 1. So we can write next step like sine of integration y minus phi x minus mu fx into fyx dx into dy. Okay, so this is our next expression. So come to the next part. So next part is what we are getting here. Just you can see here, this is the function of x and y, and this is the function of x only. So we are taking function of x outside and combining the function of x and y together. So this is only x function and this is only x function. This is taking outside and combining the x and y function values together. So we get this expression. Okay, now just simply taking the second term of this expression and simplify it. So I'm taking this expression here, minus infinite to infinite, y minus phi x fy given x dy. So now you can simply So we can write this term in form of the right hand side expression. So y of this quantity and minus phi x of this quantity, and just simply you can see here, this is what, this is expectation of y given x. Okay, and what is the next term? Next term is phi x is free from y, so you can take phi x outside. Okay, and this is what, this is density over the entire range dy. So this is the, this value becomes 1 because of the property of probability density function. So now what we get next, and we know that phi x is expected value of y given x, so we are just replacing expected value of y given x by phi x, and this second term is also phi x, then value becomes 0. Okay, so now if we are putting this value in equation number 3, then what we get? We get expected value of y minus phi x and phi x minus mu equal to 0. Then the equation number 3 becomes, you can see here, equation number 3 becomes variance of y is equal to first term expectation of y minus phi x square plus second term variance of phi x, and third term becomes 0. So third term, I just remove here third term, and now you can see here variance of y and variance of phi x. So variance of y is equal to variance of phi x plus some quantity, and this is non-negative quantity. That means variance of y have the greater value as compared to variance of phi x. This implies that variance of y is greater than or equal to variance of phi x. So this is proof that, that means if we are using sufficient statistic with unbiased estimator and we define new function phi x by conditional distribution structure, then we get minimum variance unbiased estimator by the Rao Blackwell theorem. So thank you so much to everyone for watching this lecture, and we will meet soon with new lecture and new concept. Thank you.